Hi, I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Magic. We'll look at a nice little magic trick involving a full set of dominoes. It connects directly to a Prussian village game from the 1700s. The trick is a part of Art Benjamin's Great Courses Discrete Mathematics videos, which are excellent. Here's what it looks like. I bring in a complete set of dominoes, hand a prediction to a volunteer, and ask another volunteer or two to arrange the dominoes in a string. That is, a 3 on one domino must be paired with a 3 from another domino. I disallow one standard domino play. Playing off of, for example, a double 5, do not start a string in a perpendicular direction. Just one long string. At the end, I ask the volunteers which numbers are at the beginning and end of the string. If they say, for example, 4 and 6, I ask the first volunteer to open up the piece of paper I handed out at the beginning of the trick. The paper has the numbers 4 and 6 written on it. To explain the trick, we must take a detour in time and space to the city of Königsberg in 1736. Königsberg was a Prussian city, now known as Kaliningrad in Russia, on the Pregel River. The river separated the city into two banks and two islands as shown. 7 bridges connected the different land masses. A local challenge was to find a walking route that crossed each bridge exactly once, ideally starting and ending in the same location. The great mathematician Leonhard Euler solved the problem, in the process adding graph theory to several other areas of mathematics that he transformed. Euler's solution was to abstract the problem to 4 dots, representing the land masses, and 7 lines representing the bridges. So the 2 bridges connecting the northern part of the city to the western island are these 2 lines connecting the upper dot to the left dot. What has to happen to start and finish at the same location? Well, let's focus on a particular dot, called a vertex, and count the comings and goings. If I start on the left and leave, that's 1 bridge that must be used. When I return, I need to cross a 2nd bridge. If I leave again, that's a 3rd bridge, with the return trip requiring a 4th bridge. To start and end there, I will need to cross an even number of bridges, 2 or 4 or 6 or whatever. The same logic says that the other vertices would also require an even number of bridges, coming in and going out however many times. But the vertex on the left has 5 bridges, so I can't start and finish there. The ideal path does not exist. We say now that this graph does not have an Eulerian circuit because not all vertices have even degree. Let's then try for a path that crosses each bridge once, allowing different starting and ending points. Clearly, we could start at the left vertex, using 3 bridges to leave and 2 to come back. Check the other vertices. At the top, there are 3 bridges, another odd number. If we start on the left, maybe we can end at the top, using 2 bridges to come in and 1 to leave. But the vertex on the right also has 3 bridges. If we start on the left and finish at the top, we must enter and exit the right vertex an equal number of times, so the number of bridges must be even. We can't do this one either. To summarize, to have a path that uses each line exactly once while starting and finishing at the same vertex requires every vertex to have even degree, an even number of lines. Okay, so what does this have to do with dominoes? Well, make a graph, dots and lines, where each vertex represents a number and each line represents a domino. The standard domino set uses the numbers 0 through 6, so we have 7 vertices. Then we make connections. For the domino 2, 5, we draw a line connecting the 2 and the 5. The domino 4, 6 connects the 4 and the 6, and so on. In a complete set of dominoes, all possibilities are present, so every number is connected to every other number. Well, we just learned a simple rule for determining whether there is an Eulerian circuit for a graph. Let's apply the rule to the domino graph. Each number connects to the other 6 numbers, making 6 lines, plus 2 more for the double domino connecting to itself. They're all the same and all even, so the graph does have an Eulerian circuit. But what would that look like? Let's say we start at vertex 2 and start our circuit by going to 5, and then to 3, and then to 4, and so on. The lines represent the dominoes 2, 5, 5, 3, 3, 4, and so on. In other words, the circuit around the graph corresponds to laying dominoes down in a string. But we can do this using each domino exactly once and starting and ending at the same number. A complete set of dominoes forms a complete loop. Unless, for example, you pocket the 4-6 domino, in which case your domino string will be stuck with a 4 on one end and a 6 on the other. So pocket one domino and your prediction for the string will be the numbers on that domino. If somebody objects, you've done this before and it's always 4-6 on the end. A little sleight of hand will help you out. Remove the 4-6 domino from your pocket as you're shuffling and mixing up the dominoes that were laid out. As you're doing this, palm a different domino and put it in your pocket. Just be careful not to get a double. Have them redo the string and write down your new prediction. That works pretty well. One sidebar here. Ever wonder why dominoes include zeros and go 0 through 6? It seems like 1 through 6, like a die, would be more logical. Well, the graph for a set of 1 through 6 dominoes would have every vertex with odd degree, no complete cycles, allowing fewer long paths and making the game less enjoyable. I doubt that knowledge of Eulerian circuits was involved in the decision to make dominoes 0 through 6, but it's fun having a good explanation for why 1 through 6 would be a bad choice.